Okay, so in this example we have a ladder resting against rough vertical and horizontal surfaces on a cart. A person standing on the ladder at a position for which the center of mass of the person in the ladder is at G as shown in the figure. We're told that the combined weight of the person in the ladder is W and that the cart is given an acceleration of A to the left. In this problem we're asked to determine the minimum coefficient of static friction μs between the ends of the ladder and cart required for the ladder not to slip. Okay, so since we're looking for a coefficient which is embedded into a force, it makes sense that we're going to want to treat this problem using Newton's second law. And so I need to start, as we always do, by writing a free body diagram for this system. So in this case, if we look at forces, first of all we know the weight will be acting at point G. We'll have normal forces at NB and NA, which account for the contact between the ladder and the wall. And we'll note that the tendency to slip will be downward, so we'll also have here an FB and an FA. Now in terms of our MA side of our free body diagram, we know that we're going to want, for the cart to not slip, a mass times acceleration which is congruent with that given by the cart. So to help us out, now that we have this free body diagram, we can go ahead and apply our kinetics equations. So I'll start by summing forces in the x direction and setting that equal to m times ag in the x. And if I do this using conventional xy axes, what I'm going to have here is that NB minus FA is going to equal minus MA. And because in this problem we're not given mass, we're given weight, I can rewrite this as minus W over G times A. And let's go ahead and call that equation 1. I can also sum forces in the y direction in this problem, set that equal to the acceleration at G in the y, which turns out to be 0 in this case. And what I'll get is that FB minus W plus NA is equal to 0. And we can call that equation 2. I can also sum moments about the center of mass in this problem. And this is a bit trickier due to the geometry of the problem. But if I sum moments about point G, I know that's going to equal I about G times alpha. Again, we don't want the ladder to slip, so alpha is going to be 0. And so if I look at this, assuming in this case, as we often do, a counterclockwise positive moment, I'll have that NA contributes a positive moment, and its moment arm will be given by L times the cosine of the angle theta minus the distance d. I'll note that FA creates a negative moment, and its moment arm is given by H. FB also creates a negative moment, and its moment arm is given by D. And we'll have a negative moment finally given by NB. And its moment arm length is going to be, in this case, L times the sine of the angle theta minus the height H. And we know that's going to equal, because the ladder's not going to rotate, 0. And we can call that equation 3. Now if you stare at those three equations, you quickly realize that even though we know the acceleration in this problem, we have a few too many unknowns. Namely, in this case, we have 1, 2, 3, 4 unknowns. So what we're going to have to do now is we're going to need to find some other equations to help us out. And in this case, I think it's relatively straightforward. What we need is that FA has to equal mus times NA. We can call that equation 4. And I have to have that FB is equal to mus times NB. And we can call that equation 5. So let's see what starts to happen now as we try to do some reduction on these problems and do a little bit of algebra. So if we start with equation 1, we're going to have that NB minus FA, which is mus times NA, is going to equal minus W over G times A. If I look at equation number 2, I'm going to have mus times NB minus W plus NA is going to equal 0. If I look at equation 3, I'm going to have NA times quantity L times the cosine of the angle theta minus D minus FA times H. Whoops, and I should substitute in FA. So mus times NA minus mus times MB. And by the way, there should be an H here and a D here. Minus NB times L times the sine of the angle theta minus H is equal to 0. If we look at these three equations now, we quickly realize that we have three equations with three unknowns. This is a solvable solution set. Namely, we don't know NB, we don't know mus, and we don't know NA. So we can go ahead and use our powers of algebra, which have been well developed for us at this juncture, and solve for those three quantities. we can get NA and NB, two quantities that were not explicitly asked for, but might be helpful in a design phase. And most importantly, we can get the coefficient of static friction μs, which is what you're asked to find in this problem. I know you guys are masters of algebra, so I'll just go ahead and leave us here, and simply wish you the best of luck. Take care, everybody.